goes on, you're all welcome to be there, and that's why I'm going to have the emails going out so everybody can know when that is. So you're welcome to be there, 100%. The more many hands make light work, right? And so that's what we want. You're kind of probably wondering. Sure. That- yeah. Yeah, you'll get if you're getting these meeting emails, you'll get the other ones too. I think the last one went out and it kind of had some wrong information. It's fixed. You hire the handicapped, which is me, and this is what you get. Um, what's next? Um, yeah, so and it's for everything, right? President, vice president. Um, I think we do this yearly, right? Kim, if you want to nominate someone, sure. I'm the vice president right now. I don't know was I elect. I can't. I don't know. I don't know what I've been appointed to and what I've been elected to. Here,
There is 5 elected positions: president, vice president, and then 3 members at large on the board. The 2 appointed positions are the treasurer and secretary. Correct. So we will get nominations out, and then right around the time of the December meeting, we will get the voting out, and that'll all be done through Ham Club Online. Yes, sir. Okay, we will let Mr. Kim, our webmaster, know.
one thing that I know Hand Club does is it starts sending out membership renewals, and I think it directs you to the website k7swi.org. So I followed that, and if you scroll down, it does give a link to Hand Club Online, I think. But it takes you, but yeah, but it'll land you on a registration page on Hand Club Online. So we need to figure out how to just link that to the main homepage. Maybe put 2 links: to register, become a member of the club, click here; to renew, click here. Something like that we can discuss. I don't know. I'm not that smart when it comes to links to set it up. But you know more about Hand Club Online than I do.
Correct. So we covered our upcoming events.
Um, there's no. Yeah, we talked about the auction that we planned on having for this month, the swap meet, right? Kind of the location fell through. Um, where we were going to have it, the communications just stopped for whatever reason. I don't know what happened. So unfortunately, there's not an event except, and I don't know if this may or may not happen too. We talked about when we get the repeater up there, is just letting everybody know so that we can, wherever your home might be at, call into the repeater and somebody will act as net control, whatever, take down where you're at and record how clear it's getting, just so we can have an idea of how well that repeater's working everywhere all over the valley. So that would be what we'd be doing this month. And we're hoping that we can have it up within a couple of weeks. It's just about ready to be put up there, and then once it's up there, we just put everything in and plug it up, and it should be working.
You make it sound so simple.
Yeah, I can make anything sound simple, but then it takes like 5 days to do it. If you ever go up there and look at the mounts that are on the side, I don't know who welded them. The person who
I got picture proof. I got picture proof.
Sure, whatever. I don't know who did it. The guy didn't know what he was doing. Literally, did not know what he was doing. I think he
Are
was
you
first.
sticking to your story?
It was yeah. It was his first time welding. It looks like it was his first time welding.
Okay.
Was it welding? It was googling.
Something like that.
Google weld there.
He was putting a bunch of goop stuff, whatever, with some electricity and bright lights. Had to close his eyes. Christmas party. Christmas party is going to be on the 14th of December is the plan.
Golden Corral again. We thought about doing it here, but Idaho Pizza doesn't rent this out on Fridays and Saturdays. I thought it would have been a nice idea to have it here on Saturday because we could have all of this. But again, think they're too. Yeah, I've asked. I've asked and talked to them, and yeah, they don't do it. So Golden Corral. The thought behind that is, we start at 3:30. You get there at 3:30. You're going to pay the lunch price, and dinner starts at 4. So you're getting dinner for the price of lunch. Again, there'll be a white elephant gift, right? Keep the gifts right around $20 for what you want to trade to or whatever. I'll admit mine go over 20, not by much, but keep it. There you go. Wait, for $20? Yeah, you probably could. I don't know. But yeah, so the December 14th, and I'll get that set up on the Ham Club online, so those emails can go out too, with a little bit of description on there. I'm sure there'll be some door prizes, some such going on. If you have anything that you'd like to donate to give, that's pretty cool to have as a door prize. Get with Kim. Talk to Kim about it. The reason, I don't know if you've heard about Kim or whatever, they've got some family stuff going on, and he's headed over to St. Luke's right now to visit his nephew. That's why he's not here, and that's why I'm talking to you instead of Kim. You'd rather listen to him, though, I know. Anyways, did I cover everything? I don't know how good that is.
Not very good at all.
Mine's not good. Okay. Well, let's just get on with the presentation. Again, thank you for all the donations. I mean, I can't say thank you enough because, and I'm sure Kim says, thanks a lot to this. This is really, I'm just going to toot my horn a little bit. I'm part of this club because I think it's a good group of people to be with, honestly. I count each and every one of you as my friends. Truly friends. Missing Rob and Mandy moving to Georgia, but just like they are. I mean, it doesn't matter who we are, what we are. We all get along. We all have the same type of values, and we all like to have fun playing on radios and whatever else we do. So I like it. I enjoy it. Good group of guys, and you always can call on me whenever you need to do something too, with an antenna or putting it up, taking it down. I don't mind climbing up a pole. Kim won't do it. I have no fear of heights. Literally have none. So
Both Mike and I have had our fair share, but don't want to go back up.
I'll go up. I go up every day. Steve's got the presentation. I'm going to give this to him.
So tonight's presentation is on filters, diplexers, and duplexers. For many of you, this is probably going to be very basic. So please, if you got input, please chime in. I do not by any means claim to be an expert on any of these topics. This is just stuff I have learned as I've gone on. And I'll be honest, preparing for most of these presentations, I learn more doing that than I do a lot of other things. So, some quick basic formulas and reminders. 3 dB is equal to 50% power difference. And so power 10 log 10 power in over power out is our dB, or 20 log 10 V in over V out is the same dB. Power is V squared over R. In majority of our cases, R is going to be 50 ohms. Unless we're dealing with high SWRs and other things, impedance mismatch. Filter types, there's 4 basic filter types. Filter shapes, I guess is a better way of putting that. We'll come across low pass, high pass. Low pass allowing our lower frequencies, cutting off the higher frequencies. High pass being inverse. And I have a typo there. Then we have band pass and band stop. A lot of times we'll hear in the ham world, I hear the band stop refers to as a notch filter, blocking out a very specific portion, usually used for blocking out a certain frequency of interference. Why do I need filters? If anybody's ever been up to Bogus Basin and higher on a handheld trying to activate the POTA entity up there, you'll probably know you're not hearing much back. Desensing the receiver is one of the major reasons for filters. Field day operations, competition operations, where you've got multiple radios running close to each other, is another prime example where we use filters. Correct. Yeah, many of you will recognize that from Winter Field Day out at Curtis Park. As an FYI, that is Curtis Park in Caldwell. It will be our operating location again this year for Winter Field Day, keeping it close in the valley so those people can come out and enjoy it. We can get those who can't come overnight and stuff. It's still someplace close and easy to access. It's winter, but it's not as cold as Bonneville Point with the wind blowing. Why else do I need filters? First two we're talking on primarily on the receive side. The opposite is true also for harmonics on the transmit side. If you're buying two of those $10 bow things, you're probably going to need the filter for transmitting on the harmonic, so you're not transmitting the harmonics on the output. There's three common filter constructions that I have come across in ham radio. There's probably more. I do know there's a four. We'll talk in a second on the element one. Stub filters, probably the simplest and easiest to build and get into. Element filters, well, if you open the inside one of these Dune Stars, they're going to look very similar to the image there. And then cavity filters. Element filters come in, are sometimes classified into dispersed and clumped elements. Typically when they're saying lumped element, it's all that has been put onto a single IC by somebody who specializes in that for insertion into the radios and stuff. Two types of stub filters. We've got an open stub filter and a shorted stub filter. Going to talk first about the open-ended. So, as the name implies, the end of the stub here is going to be open. Just cut off the ground, and the conductor or the shield and the conductor are not connected. On leg one, we'll output a standard sine wave. Once it hits the T there, it's going to then go to half the power because it's split there, one leg going straight out and then one down the leg. Going down leg two there, because typically they're a quarter wave, we get a quarter wave offset. At the end being open, we do not get any phase shift when it's an open-ended. So as it returns down the leg, it then shifts another 90 degrees. So a total of 100. By the time it gets back to the T, it's 180 out, and it's going to act as a band stopper notch filter for the input. Any questions? Depends. A quarter wave open is going to become a notch filter for that frequency. So if I'm planning on operating 20 and my neighbor's operating 10 and he's causing interference, my filter is going to be set up at a quarter wave for 10 because it's a band stopper notch filter. If it is an open-ended, yes, very, very valid point, and thank you for pointing that out. The velocity factor of the coax does play into that length of what that actual length is. Correct. No. Yep. This one here is. Yep. I'm not sure if this is an open or shorted because it looks like it's been covered with something so nobody gets RF burn off the tip of it. But yeah, it's literally take your. Yep. So yes, and each of your standard coax types have a standard velocity factor that can be looked up in the tables. Typically, you'll want to start long, and then you can just trim it in, and you'll see the notch come in, notch or bandpass on your VNA that you can move it where you need to. A shorted end stub is like I said, starts there. First leg, we go to half the power because it splits to go half the power. Down leg 2, we go 90 degrees because there again it's a quarter, close to a quarter wave, acts to quarter wavelength. The shorted end will cause a reflection of 180 degrees on your. Then we come back to leg down the leg again. You add those two 90s and 180 up, and we're giving our half back, and it passes through. So it becomes a band pass filter for it. Correct. Okay. Yeah. So, and it's interesting. The table here shows a quarter of 160 shorted. It's going to pass 160, null everything else. But you get down to a quarter wave shorted. It's going to pass 40 and 15, but stop your 20 and 10 due to the harmonics of the frequencies and becoming a half wave at 1 versus a quarter. All filters you are going to lose some power. My understanding, and somebody correct me if I'm wrong here, a stub filter is not extremely lossy compared to some other types of filters. Yes, Mike. Okay. Yep. If you were transmitting this being assuming we're talking a bandpass filter. So if I transmit 100 watts, it's going to split at the T. 50 watts is going to go down and come back and then rejoin the original 50 and go down and make 100 out. Now, my understanding here is if you transmit 100 watts into a notch filter, say my notch filter's tuned to reject 40 meters, and I transmit 40 meters in, most of that's going to be reflected back at your radio. Yes. Correct. Yes. Yes. Very, very good question. And that's one of those, as I see it, we talked about the three constructions of filters. There's kind of three different ways a filter will work too. There is basically reflecting it back, which the stub filters are doing. The element filters are going to dissipate it to ground, and then your cavity filters are a resonance-based filter. And we'll touch on that here in a little bit more. Yes. So why would I choose a stub filter? They're simple, they're fairly easy to tune, and they're an entry-level filter that majority of people have the parts to build one sitting around. They could very easily be thrown together in a tactile situation, like whether it be like a field day situation or an MCOM situation. You could very easily put one together and deploy one based on parts, where the other filters we're going to talk about are stuff you kind of have to have the exact specific one you need there beforehand. Cons, to my knowledge, they are a lower Q filter than a majority of filters. And I forgot to put the slide in. So when we talk about Q on a filter, we're talking about how steep the sides and cutoff frequency respond. So a higher Q filter is going to be a very sharp peak, where a lower Q filter is going to be more like a little hill. Element filters. This is when I think of somebody saying I'm putting together a filter, this is what I most commonly think of. There are several different topologies, base topologies for them. We'll talk about how the order of the filter applies, type of filters, and the pros and cons. The construction of how they work, an element filter is primarily a clumping of capacitors and inductors. As capacitors, as the frequency goes up, they become less and less inductance. So they allow the electricity to flow easier and easier. Inversely, as the frequency goes up, inductors start to oppose the flow of electricity more and more. Our topology, the two major topologies I've seen are the T topology, where you've got two inductors or two capacitors, separate them on top with one of the opposite coming down in the leg. Opposite is the pi, where it's the top is 1 separated by 2. They're functionally, I am not aware of a huge difference. I think the primarily is reason you go one way or another is the availability of getting stock components to be able to build one way or another with capacitors, inductors. Our order of when we refer to the order of a element filter, we're talking about, for lack of a better description, the number of components in there or how many filters we've put in series inside that enclosure. Because you can see, here, a 3 order, we've got our 3 parts. We go to a 5th order, our cutoff frequency is the same here at 100 megahertz, but our slope is a lot greater. The blue line on these charts is representing our insertion loss. The pink line is our reflection coefficient. So, what? Insertion loss is how much power we're going to lose from port A to port B. So if in this case, talking this one here, at 100 megahertz, I'm going to lose 3 dB of power from my antenna to my radio, or vice versa. Now I can say at 100 megahertz, 3 dB, because I know the cutoff frequency of these filters when I put the simulation in here was 100 megahertz. And our cutoff frequency is typically referred to at the 3 dB point, or where our power is cut in half. Yes, if I was to put this filter in line, so we go, for simulation purposes, you've got a voltage source, the 50 ohm resistor at the front and end represent the 50 ohm loads impedance of our two systems for simulation purposes. So putting this in line, we're going to start out, as the frequency rises, we're going to start out with all of our power, or the majority of our power, being transmitted in a theoretical world, and then at 100 megahertz it's going to be 3 dB, and then it's going to go down from there to even less and less power making it through. Now I talk about a reflection coefficient, that where that comes into play is our SWR. This filter reflects back. VWSWR is 1 plus the absolute value of your reflection coefficient divided by 1 minus the absolute value of your reflection coefficient. So as our reflection coefficient is 0 up here, we are going to have a 1-to-1 SWR as it represents. But we're going to get we're not going to get much efficiency through. But as we go down to the low end here, we're going to have a SWR that is not 1-to-1 being induced by that filter being installed. So just saying, if throwing it out there, if I've got a low pass filter with a cutoff frequency at 10 meters, and I'm going to go run it, but I'm having interference, something causing interference on my 440, or vice versa, they're not going to be just taking any low pass filter and putting it in elsewhere may cause you other issues because of this reflection coefficient. Even though it's going to allow the signals you want through and block signals, they still need to be tuned for the frequency they're used in to avoid SWR issues. Yes, sir. Okay. Yep. Yep. Yes. When you stack two AM filters in series, you are going to increase your attenuation. You're also going to increase your Q factor. But the challenge is, if you're trying to work weak signals, you've also increased your insertion loss. So you on the band you're trying to get at. So there's a trade-off there. There are multiple different types of or theories of how to lay out all your components for your filters. If you go to an ARRL handbook, there are tables in there that'll tell you for this with the correction factor for frequency that here are your capacitors and resistors to use for this cutoff, not resistors, capacitors and inductors to use for these cutoff frequencies and stuff. You'll notice both of these up here are 5-element pi and low-pass filters. One is a Butterworth filter, and one is a Chebyshev filter, and I'm sure I probably just slaughtered that name. A Butterworth filter is typically known for a very smooth insertion loss, where a Chebyshev filter, you'll notice it's got a lot higher Q factor, but you get some unique points in your insertion loss and bandpass ripples, they refer to it. It's hard to see here in this particular one, but if you were able to zoom in, you'd be getting some ripple there in your insertion loss also. So there's, depending on the type or topology, however you want to word it, there's trade-offs one way or another of which way they go. Yes, sir. Correct. Yes. Correct. And that's, yeah, so back to that being tuned to the right spots. Like I said, Chebysev's got a lot higher Q factor to it. The Chebyshev and the Butterworths and all them, can also be made into a bandpass. When you see a bandpass, a lot of times, they can either be a low pass and a high pass put in series right in front and behind of each other, or you will sometimes see a capacitor and an inductor in parallel on each leg. So they work in the factors that way. Why would I choose a element filter? Simple, fairly easy to tune. The hard part about tuning them is, especially the kits you build yourself, is the inductors are always, you got to get in there, wiggle with them. And the capacitance of the case, you have to close them, open them to test them. But they're fairly durable compared to cavity filters. They're small, as you can see. Brian was talking about the 15 meter filter. Happens to be actually the one that's just sitting here. That's the 15 meter filter. They are an intermediate level DIY project. You can buy kits to build them, or you can buy them complete. The kits, you've got to wind your own toroids. They're a fair bit of work, but nothing rocket science about them. The hardest part there is probably dealing with the fine components and measuring the capacitors and stuff out. Having the right tools makes that fairly easy. Cons? Yes, sir. Okay. Ham Nation? Okay. Yeah. Yep. Back to that discussion and question earlier. What happens to the energy? So as these are low pass filters, you start getting into the high pass range, or the higher frequencies. The impedance of those capacitors is going to go down, which basically allows it to short to ground. It's not going to be the VSWR is not going to be the best, but that's how it's going to dissipate it. You run the current through the components that are not rated for, and we let magic smoke out. Yes. Very good point. Thank you for that insight. One thing, when we talking about bandpass and notch filters in particular, and even on low pass and high pass filters, they are not always symmetrical. So your loss from port 1 to port 2 may not be the same as from port 2 to port 1. Just due to the nature of the components and everything inside them, they may act different whether you put them in one way or the other. Yep. Primarily, these examples, they are symmetric, but I have seen them where the components are not symmetric as they go down the chain. So that's going to affect the stages and how it filters and stuff. And just the manufacturing variance of all the components. These are your filters. Like I said, the complete HF ones can be had in 200 watts for under $100 a band. They're mid-level on cost, like I said, moderate insertion loss depending on the components. The numbers I typically see is you're usually around 1 dB insertion loss in practicality on a element filter. depending on how all the components and everything inside are. Okay. Okay. Yep. Okay. So they may have gone up, but yep. The last type of filter we typically see in ham radio, or I have typically seen, is a cavity filter. What I know about them, they're an extremely high Q filter. They're a lot of times called cans, as you can see why, and they're resonance based. I don't understand how they work. I'll be honest. I do know how you adjust them, but the theory behind the adjustment, I'm not 100% sure. Pros on cavity filters, they're very high Q. So when you're operating in real close to other frequencies, they work well. You see them a lot of times in commercial applications because of that high Q and as much stuff as they have banked together. Cons: size, weight, and cost. And the one I didn't put here on the cons is they can be fragile. They're not something that's easy to pick up, throw in your go kit, take around, unload it, throw it in the back of your pickup, move around. They can get damaged and or out of tune fairly easy that way, from what I have been told. Diplexers, triplexers are typical. Correct me here if I'm wrong, if I misunderstand them. Typical application is multiple antenna systems. So say I've got a 6-meter antenna and a 2-meter antenna and my 7100, and a HF antenna, and my 7100 has a VHF port for my 2-meter 70 center, and my HF ports for my 6-meter and all the HF. I can run a diplexer in there to hook my dipole and 6-meter antenna together to bring into the 7100. That is the typical application. They are from my understanding, they're typically about 50 dB 40 to 50 dB isolation between ports or bands. They can be used to tie multiple radios to a single antenna, but you're most likely going to need additional filtering in there because you want about 80 to 90 dB of isolation between one radio and another radio. Okay. Okay. What are you referring to? Multiple radios on? Because that is typically multi-band antenna, and we're only receiving or transmitting on one band at a time. Yes, correct. Think of a fan dipole. A fan dipole has one leg for each of the frequencies that it's using. Yes, they all interact together, but one leg is primarily for each frequency. Your Yagi is very similar. Very good question. Thank you for asking the loaded question here. Okay. Yes, they're okay. So yes, there's two scenarios here. We'll talk the first, multiple antennas to one radio. If we recall back, if I've got three antennas, or let's just say two antennas that are both 50 ohms impedance, and I connect them with a T, I now have 250 ohms in parallel, which is not going to be 50 ohms seen by my radio. Yes. Now the other question is, and you hit your question about the T, and the other scenario, you're talking about one antenna, multiple radios. You want to run a triplexer, diplexer with bandpass filters to prevent my 100 watts from on 20 meters from hitting your front end when you're operating 40 meters. So in the inverse, that's why we run them when we're running multiple radios to a single antenna. And that's why when we're running, a lot of times we have this triplexer and then the bandpass filters in line also to hit that 80 to 90 dB isolation between radios. Yes. Yep. Very good point. Now, why can't you set it with a T? So if I've got this T coming from my antenna, you're operating 20 meters, you're operating 40 meters. Why can't I just put a 20 meter bandpass filter on this side of the antenna and a 40 meter bandpass on this side to the respective radios? Back to the impedance matching. When they design a diplexer or diplexer, triplexer, etc., they consider that I've got three systems all coming back, so it's all three of them are impedance matched on both ports. The same thing if you are testing one, you want to put a dummy load on the unused ports, or it will throw your results off also because it's designed to have a 50 ohm impedance on each port to match all three of those. What is inside of a diplexer? Well, this is particularly this one here. They luckily put their charts up there from testing online, so I borrowed them. You'll notice on the 2 meter side, we have a low pass filter. And based on the response here in the spike, it's a variation of a Chevsveb type filter in there, most likely. You go over to the 70 centimeter side, it's a high pass filter. So it is two filters in there, but they have impedance matched them so you maintain 50 ohms on all three ports. Duplexers. Duplexers and diplexers are very similar function. The key distinction is a duplexer is typically in band. Both your transmit and receive are in the same band to one output antenna. Primarily used for repeater locations. Here you'll see what's referred to as a 4, because it's got 1, 2, 3, 4 cans or cavities, a 4-cavity filter. The more cavities your duplexer has, the higher separation in Q it has. Now, typically you see these a lot in GMRS, but they will sometimes work depending on the quality of them and what they're set up for in the ham band. But if you're familiar with the GMRS frequencies, the split between on a repeater is higher than it is on the ham band. And the split on relative to the frequency the split on 440 is proportionally bigger than it is on 2 meters. So that's why you can see smaller duplexers in 70 centimeters with less cans. Now the can dimensions, back to the cavity filter, the can dimensions are relative to the frequency to get all the resonance in there. And now this is a six element or 6 cavity, and 2 meter repeater there. One thing of note is you'll sit here and look at this and go, that looks sloppy with all that extra wire there. For the phasing of all the cavities, the wire lengths between them has to be a particular factor also. Yes. Those are going to be about that, if I remember right, are going to be about a 7-inch diameter by about 1.5 feet. I'm sorry, about 2.5 feet long, for a 2 meter can, based on this having the specs up for that Sinclair one I took a picture of earlier. Yes, sir. Okay. Yes. Cor- correct. So yes. Correct. Yep. Correct. Yep. And I did not know that. I appreciate the comment about the band pass, band reject. I didn't realize that they were set up to pass and reject at the same both sides. So yeah, but you look at this one here, it comes out, goes into cavity 1, out of cavity 1 into cavity 2, and out for your high side, and same side for your low side, so they can be operated in full duplex when they're up on the repeater side. Yep. As is alluded to, size is proportional to frequency. That is a set of what they claim are 6-meter cans. So they are. So this is why many 6-meter repeater sites will work in a dispersed type setup where they will have receive at location A, linked over to location B, and with a different frequency, and then transmit from location B, is because the cans just get to be unruly. Correct. Yep. Okay. Right. Okay. Yeah. Interesting. I've not heard of that. I'd heard of circulators before. There again, they're part of that RF black magic that I don't fully grasp. Okay. I I will agree with you. Yep. No. Any questions? No. 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 I learned. Thank you. Correct. I can put those up. Yep, on the Facebook, and it will also be up on the whole presentation. Will be up on our YouTube channel also, for reference later, or for those who aren't able to make our meetings. We do try and record them, put up there. I will try and pull those out and put them on there. Yep. Very good point. Thank you. So that's all we had for this week, this month. Um, Anything else, Brian? I'll turn the microphone over to you.
Kim, where are you?